Swayam Prabha. Digital India. Educated India.
Actually, we will do slightly different. The second would be interrupt service routines. Next would be virtual memory, and the last will be on what we call as task switching. These four are very important concepts which you need to understand to finally appreciate why certain things are done by the operating system and the compilers, right. So, if you want to have a good understanding of that, then understanding these four concepts in detail is a must. Okay. So, each will carry 20 marks. We will try to see again like in the previous semester course, I want you to understand it first. So, just getting a working code will not give you marks, but we will have a very strict viva voce. Okay. So, we will ask you a lot of conceptual questions there, and we want you to answer those questions. So, this 20 marks would be directly proportional to how well you handle the viva voce. Okay. So, understand and do the code. I do not even mind you know, I will not use the word copying, I will be diplomatic, discussing with yourself and doing the code. Okay. So, I do not really mind that, but when it comes to viva voce, it is going to be one on one, and I want you to answer those questions very clearly. Okay. That we will check your thoroughness there. Okay. So, this is not more of a skill, but it is more of an understanding that we want to develop through this lab. Okay. So, when we teach you these things, like we will cover some background material for each one of these four, and that will happen in the first 45 minutes of each lab course. Okay. So, everywhere there will be, I will talk about influence of compilers on segmentation and influence of operating system on segmentation, right. Similarly, influence of compilers on ISRs and OS on ISRs. ISR essentially stands for interrupt service routine. Okay. The way you can show yourself as high funda, the easiest way of showing yourself as high funda is to have a lot of these abbreviations memorized. So, ISR, ASR, you can talk an entire talk you can give just with abbreviations. Okay. Also virtual memory and then task switching. So, what I will do today is that I will now talk for another half an hour, and I will tell you what each assignment, what it means to complete this assignment, what are the objectives of this assignment, why these four things that I have put here. Okay. When a program wants to get executed, the program essentially will have three blocks. So, your a.out, if you go and see how it is getting executed, it needs three different parts of memory, right. So, let us just start when we want to execute a program. So, each instruction will undergo 5 different, each execution of an instruction will be in 5 phases, correct. What are those phases? I will fetch the instruction and increment the program counter. Next, decode the instruction, fetch the data, execute the instruction and store back the results. Okay. So, at least 3 of this, right, fetching the instruction, fetching the data, storing back the result, at least 3 stages I may be touching the memory, right. So, a program essentially has 3 components. One is the instruction that we are trying to execute, the second is the data that I am going to use, and the third is obviously the stack. Why do we need the stack? Again we will explain in more detail. We have done quite a bit of stack work in our 3rd semester course, right. Lot of stack you have seen, both in your data structure plus in the foundation to computer system design. We will see more of that stack here. So, there are 3 different segments that are necessary when you want to execute a program, right. and two important things come up. One is that when I look at a mail server, for example, there are two processes that are executing together, right. So, one process will execute, halfway in its execution it may be pulled out, another process will go and start executing, then only it can give a feeling that it is serving all of you, right. If 4 of you log into a Gmail server, Google server, right, then you start typing the email till you finish your email, the other fellow has to wait, right, then you get really frustrated. There will be 1 million users. So the entire CPU is scheduled so that you get some time, then you are pulled out, then he gets some time. So everybody has a feeling that the server is giving some service to it, right. So when more than one process, what is a process? Program in execution, right. So I have hello world.c, that is a C program, I compile it, I get a.out, that is an executable program. So I press ./a.out and press enter, then that executable program starts executing, then it becomes a process. So a process is nothing but a program in execution. Now there will be several programs in execution, right. So each program, each process will have its own code, its own data and its own stack, right. So when I look at the memory, there will be P1's instruction, P1's data, P1 stack, then there will be P2 instruction, P2 data, P2 stack. Now I will have P3 instruction, P3 data, P3 stack. When P3 came, I did not have contiguous memory locations, so right, it need not be contiguous. So there are 3 segments, that is why we call it as segmentation. There are 3 different segments that are associated with each program, right, each process. Now I need to protect these segments, correct. For example, P1 should not go and look into P2's instruction data or stack or P3's instruction data or stack. Are you getting this? P1, then what will happen? It may go and it can change something in P1, P2's data or P2's instruction, and then the correctness of execution will not be there. When I compile a program and I know it is correct, I expect it to execute correctly. No external factor should not come and change the execution of my program. That is what I guarantee to the user, right. So since you have coded a program and you are syntactically and semantically correct, syntax means the grammar, semantics means is the meaning, the logic, okay. You are syntactically and semantically correct and you start executing in my machine, the operating system should ensure that your program will execute in the way you want. If some other program comes and changes your execution or changes your data, then you will not get the desired result. So one of the responsibility of the operating system is to see that P1 should not go and access P2's instruction or P2's data or stack. P1 should not have access to the other thing, right. So this is what we call as inter-process protection. I call this as inter-process protection. One process data, stack and code is protected or isolated from the other process instruction data and stack, okay. Now how do we achieve this? We achieve this through what we call as segmentation. One of the ways of achieving is through segmentation. The next important requirement from the operating system end is that myself, so what is a stack, right. So what are the 2 operations on the stack? One at a time, push and pop. So let us say this is stack and this is data, right, for P1. Now I am keeping pushing into the stack, push, 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 push. Then what happens? I go and push into the data of that fellow, right, into myself. I am pushing and I go and overwrite my data, push, everything is gone. Are you able to follow what I am saying, right? So, I start pushing into my stack, I have access to my data, my code and my stack, correct. So, I start pushing and I keep overwriting into my data, I start overwriting into my instruction, right. Then what happens, my entire program is execution is completely gone, right. Similarly, I start executing program count. What is a program counter? Program counter points to the next instruction that we need to execute. Now what will happen, I keep on executing one after another and I start executing something from the data. I start considering my data as a instruction. So I keep executing and I pass the boundary and some mistake happen, I start executing from data. Now these things your operating system should curtail. If it has given me this much amount of stack, if I overshoot the stack, it should say stack overflow. If I start executing outside my segment, then it should say segmentation fault, seg fault, core dump, all these things you have seen, right? Yes or not? Yes. So core dump, all these things should come. So who is giving this? The operating system should give. Now let us go into one fundamental question. I think one of you asked, I don't know who asked this question last time. So core dump, that comment is coming, right? Who will give that core dump comment? Who is printing that comment? Core dump, segmentation fault, who is printing it? Compiler. Some program in execution only can print it, so operating system is printing it. But when it is printing it, when your program executes and you do some error, the operating system comes and prints for you. So suppose I have only one CPU, right? This was happening even when I did programming, right, where there was only one CPU. In that CPU, right, in that CPU, my program is running. The program that is going to do a seg fault, right, that is going to do that mistake, that program is running and it did that mistake, right. How will the operating system come and print? It is also a software, it should also execute to go and print something, right. I should also execute to print something. So operating system is a software which is on your memory RAM. My program is currently executing here, I did a mistake, but now you go and say that mistake is the mistake that you have done, that mistake, what that mistake is being printed by the operating system. How? You are understanding this? Operating system is also a software, it has to execute to go and print an error message, correct. Now I am executing, there is only one CPU, operating system obviously cannot execute there, I am executing, I did a mistake, and then there is a statement, segmentation violation or core dump, whatever, but you say that the operating system comes and prints there. How can it do? Are you getting my question? Yes or no? Yes. Now you tell me how.
Program provides some kind of callback so that when it encounters this
No, how will I know that I have done a mistake? I am an instruction that I do by divide by 0. So how will I know that I have done a mistake? You are not writing, right? You are not writing callback routines and all inside. You just write a program which will do whatever you want it to do. And there some mistake has happened. Right? Okay. The point is, I need the hardware support for it. So when I do a mistake, the hardware will catch and then transfer control. Hey, you have done a mistake, stop. It will throw you out of the CPU, bring in the operating system and tell operating system, hey, this guy has done some mistake, go and attend to it. Then the operating system will find out what mistake you have done and it will go and print it. So there is a switch from your program to operating system. You are understanding this, correct? So when you do a mistake, when you do a divide by 0, so a division instruction comes to the arithmetic logic unit ALU with the denominator as 0, then immediately it will stop your execution. You are not fit to be executor, you don't know how to even divide. So it will throw you out, it will go and call the operating system and say this fellow is trying to do something, why don't you attend to it. So the operating system will be loaded. So your program will go out to the RAM and the operating system will get loaded, and then operating system will start executing, and then it will find out what error it is and then it will give, right. So for me to so the thing that we are now talking of here, if you call that the earlier one as inter-process protection, what is this? Intra-process protection. Right, intra-process protection. I tried to overgrow my stack. I have been given some space, but I tried to overgrow that. I overwrite into my data, I overwrite into my instruction memory, correct? Now somebody has to stop me. So how will the architecture stop you, and how will the control go to the operating system? So what is the, so this is a nice this entire handling of this is done jointly by the hardware and the operating system. Now what you need to understand is what is done by the hardware and what is done by the operating system. You need to have a very clear idea, correct? Then you will appreciate how these things are going to happen. So before that, some way I should know that I am overshooting my stack or I am overshooting my execution, right? My instruction is only 2000 bytes, I am trying to execute something more than that 2000 bytes, or my stack is only 500 bytes, I am going more than 500 bytes, right. My data will start from here and end here, but I am now overshooting it. Somewhere I should detect that I am overshooting it, right. And those things, that deduction is basically done using segmentation, right. So to sum up, segmentation does two things. One is inter-process protection. You are process 1, you are process 2, you cannot see his data, code and stack, and you cannot see his code, data and stack. You cannot execute or look into it. Perfect isolation, like putting one big barrier wall in between. That is number 1. That is inter-process protection. The next one is intra-process protection, where I have access to my instruction data stack, but I can't overgrow my stack, I can't keep executing beyond my instructions segment, I can't access data beyond. So for example, let us take this for P2, this is 1000, this is 1000, this is 1500, this is 3500, this is 4500 for example. So I can't store more than 1000 bytes in my stack. I can't access data which is before 1500 or after 3500. All my data should be there, and all the instructions I execute as P2, right, should be in the range between 1000 and 1499, right. If I do something, if I start executing something before 1000 or after 1499, hardware should catch me. How will it catch? Segmentation will give you a methodology for catching, okay. So this is what we will learn in the segmentation. The next thing that we will learn is the interrupt service routine. We will do interrupt ISR next, right? I think that will be better. Okay. So we will do interrupt service routine. So interrupts. So this interrupt has come in the literature, but I will try to change that. I will call it as exceptions. Exceptions are of two types. Traps and interrupts. Okay. So there are n different books, and n different books call it in n different ways. Okay. But let us stick to this terminology, and this is much more neater than what I have seen outside. So exception, what do you mean by exceptional scenario? Today is an exceptional day means what? Something that is not normal has happened, right? Something abnormal has happened. So when you start executing a program, normally it should execute, but something different than what you expect happen, then it is an exceptional scenario. This exception can happen due to two things. One is called trap, another is called interrupt. Trap, I am trapped, I am interrupted. So what is the difference between I am trapped and I am interrupted? Somebody is trapped, somebody, when you are getting trapped. So you do something and you fall into some problem, that is called trapping, right? Like divide by 0 is my problem here, it is not the operating system's problem. I start executing and ready I put a 0 in the denominator, okay. So it is not operating system's problem, my problem, correct. So this is a trap. I start overgrowing my stack, right. So you had given me only say 1000 locations, I put 1001 byte into that, okay. So that is again a trap, because it is my thing, right. It is my mistake as a process, right. I go and start seeing his code, I want to copy his code, I go and start seeing his code, that is again my mistake, correct. So I am not supposed to do some things and I start doing it, then it is a trap, and the hardware, my architecture should find out that I am trying to do something which I am not supposed to do, catch me and go and take me to the operating system and say this fellow is doing some fraud, okay. You are getting this, right. So that is what we call as a trap, okay. I am doing all correctly, some keyboard is trying to give an interrupt, some disk is trying to give an interrupt, there is an urgent thing, somebody is pressing Ctrl C, somebody has gone sat on top of the keyboard, okay. So this is not my mistake, so the interrupt is coming from some external source, some timer is giving interrupt, get out, okay. So this is all this is not my problem, it is coming from some external, and that is called an interrupt, okay. The moment there is a trap or there is an interrupt, immediately what will happen, the hardware will shut down this process and bring the operating system into existence. The operating system will go and service your trap or service your interrupt. Are you getting this, right? What do you mean by servicing your trap or servicing an interrupt? If you are doing divide by 0, it will say division by 0 error, chuck, throw you out, okay, right. If it is a stack overflow, it says stack overflow, if it is a segmentation, seg fault, core dump, it can give you and go off, okay. So but there are cases which we will see where when there is a trap, then it will say no wait, it will go and do something and allow you to continue, right. There are scenarios, we will see that. So all exceptional scenarios that you land up because of your mistake as a process, you call it as a trap. All exceptional scenarios due to external sources, that you call it as interrupt. Am I clear? Now whenever there is a trap, whenever there is an interrupt, we need to service, the operating system has to come in and service. Who will detect the interrupt or the trap? The hardware will detect the interrupt or the trap, and it is the hardware is also responsible for transferring control to a part of the operating system. That part will start executing and it will do the service. This whole thing is what you will learn in your second assignment, namely interrupt service routing. Clear? Okay. Now the third is virtual memory. When you write a program, do you really care about how much memory is there? No. When you write a program, you do not care about lot of things. You do not care about how much memory is there, what is the compiler, what everything, right. One of the important thing is you do not care about what the memory is, right. Suppose you are given a 32-bit architecture, what is the maximum addressable memory? 4 GB, 2 power 32 bytes. So that it will be byte addressable architecture. What do you mean by byte addressable architecture? Every byte can be individually addressed. So if I have a 32-bit byte addressable architecture, that means I could store up to 2 power 32 bytes. So 4 GB RAM I can have. Within that 4 GB, some will be occupied by some process, some will be occupied by some other process. So many things will be occupied by so many processes, correct? And your process will occupy only some part of the memory, but you can still write a program which is as large as 4 GB in terms of it can handle huge data, it can handle huge stack and some code, okay. I can have a very big program and still get it executed on a machine which has physical memory of even 2 GB. Correct? I could still have a 4 GB size program execute on a RAM of size 2 GB. So as far as the programmer is concerned, the operating system says, hey, there is 4 GB available to you. So the programmer assumes that there is 4 GB and he writes the program. The compiler assumes that it is 4 GB and it compiles the program. Correct? Now the operating system it has only say 2 GB RAM in which it can give probably say some 512 KB for or 512 MB for this program. Within that 512 MB it will somehow execute that 4 GB program and give back. So as far as so how does it happen? That is what we are going to learn in virtual memory, right. So as far as the programmer is concerned, he is not bothered about how much physical RAM is there. He is given, the operating system presents a view of 4 GB both for the programmer and for the compiler. Compiler assumes that there is 4 GB, programmer assumes that there is 4 GB and he writes the program. The program gets executed, right. The operating system will take care of executing a 4 GB RAM, 4 GB program on say a 512 MB RAM, okay. How does it happen? This cannot happen again with just the operating system support, right. There is a hardware support that is needed and an operating system support that is needed. So we will understand what the hardware does and what the operating system does with respect to virtual memory. And the last thing is about what we call as task switching. So what is task switching? So if you look at Linux, right, there is something called supervisor mode, root, and there is some normal user. Root is sort of dada, okay. Today all of you do every action with your mobile phone, right. Those days when all programs have to be written and you forget your password in your in your DCF, right. Root is God, okay. Night you should call him, say come reset here, I forgot my password. He will abuse you. All this you should take, what beautiful words here, come on. Now you don't need all, you have your personal laptop and first your fathers are rich to give you a laptop. Second thing is, means that it's your father's money, right? So use it properly, okay. Second thing, that you need not, now the notion of a DCF is gone, right. At last semester assignment you did in your laptop, correct? So lab is in the lap, okay, right. So now this semester also you can do it here. You need not actually go to a lab to do a computer science lab, okay, fine. So but those days root is, and even today when you look at major infrastructures today, like your mail servers, right, your CSV mail server. CSV is a small thing, but if you look at a bank mail server, right, or a bank database, so the admin is a very powerful guy, right. So there are certain things that you can do as an administrator, there are certain things that you can do as a normal user. So the entire system should have two parts. One is the supervisor mode, or two modes I should say. One is the supervisor mode, another is the user mode. So all the programs, normal user program run in the user mode, while all some very important things like accessing devices etc. will happen in the supervisor mode. So as a program, right, as a process, I can belong to the operating system, I can also belong to a normal user. So the process can be classified as a user process or a OS process. The OS process runs in a different mode, the user process runs in some different mode, right. So each process has a privilege. If I am a OS process, I am a little more dada than the normal user process, correct? So every process has something called a privilege level, right? So in a typical 4-tier operating system, okay, there is something called kernel that inside. After that there would be some system programs like device drivers, etc. Then there will be some middleware like your runtime environments, the virtual machine you saw last time, right? So those type of things, or your compilers, etc. So these are some development layer, development aids, right? Or we can call it as middleware, and above this will sit your application program. Right? So there is privilege level 0, privilege level 1, privilege level 2, privilege level 3. The most powerful is the kernel, followed by device driver, followed by development aids, followed by application programs. So this is what you call as a tiered operating system. Not tired, or multi-tiered operating system. Tier means it's multi, right? Tiered operating system. Fine. Okay. So the architecture, what is the support of the architecture for maintaining these privilege levels? Every process should be associated with one of these privilege levels. I am a process means, am I a process of privilege level 3 or 2 or 1 or 0? Somewhere I have to maintain that information. And when I want to switch from one privilege level to another privilege level, I should do it with some amount of care. I got arbitrarily switched. Then what happens? If I could arbitrarily switch from privilege level 3 to privilege level 0, then I become the super user and change all your passwords. Correct? So there should be some amount of protection that is necessary. So all these things basically, so how to maintain these privilege levels and how to switch from one privilege level to another privilege level, these are the things that we will learn in the 4th assignment, which is task switching. Okay. Now as you see here, we have been more or less, I have been talking about one point very, very clearly here, right? All these 4 assignments finally has one flavor, which is what we call as the security, right? So I think I have told in the previous course, if you look at 1980 to 90, what was the thrust in computing? Engineering computations, okay? How do I solve Runge-Kutta method fast? How will I compute cos hyperbolic fast? How will I do atmospheric weather calculations fast? These are all the big things. So they will talk about how many million instructions I can do per second, blah, blah. 1990 to whatever, 2000, the whole story was media, right? Jurassic Park, how will I shoot movies, how will I do all multimedia, all these things. So it was all how to attract a consumer towards computing, a non-computing consumer to computing, right? So to buy a computer, basically media players, all these things. Consumer electronics came up in a big way, where computers got this. 2000 to 2010, this is all mobile, correct? Now 2010 to 2033, here I am going to retire. This is going to be security. Right? Actually 34. Okay, because now you have start using with all the cashless and all these things and coming in place. I think that's the way economy is going to grow. That's the way world is going to move. So it's going towards. So you are going to do a lot of e-commerce. Your health is going to get maintained by your mobile phone. It's already very close to your heart, okay, right? More closer than your girlfriend or boyfriend, right? Or wife, okay, no problem. Right? Right? So, now when you have started using these things in a great way, then there's lot of things that we need to do so that your confidential data, other things are not compromised, okay? It's very, very important. And so security is something like, it's like a habit which should, suppose you have been sleeping in every CO class, on the last class I say keep awake, no, it will be very difficult. So in the initial days itself you should get used to a habit, not at the end. Now unfortunately last 30-40 years computers have been in existence, nobody gave a damn for security. Suddenly one fine day you say I want to make this secure. I have 10 million lines of operating system and middleware code and executing on 1 billion transistors. Now why do they talk about security, right? I want to retrofit security into this. Security is a habit, and at the age of 50 you try to, for a computer, you are trying to say now you inculcate this habit in a very big way. It's not going to happen so easily, right? So first thing is, first people should start talking about security in the courses, right? That itself we have not talked, right? Today can you buy a CPU with a single core? No. Right, CPU with a single core, the 8085 something is now $4,000 because it's ethnic value. Okay, so okay, the last 50 left out and they will sell it. Okay, now we have multiple cores. Now how many, if you just take sigma of across the world university curriculum, including all our own courses, how many courses are teaching parallel algorithms? You learn data structure, you learn compiler, even what I taught you. Did I tell about parallel, how to do this in parallel? No, we are only still talking about sequential programming, correct? This multi-core started somewhere in 2004, 12 years, curriculums have not matured to talk about concurrent programming at all, whatever be that reason, okay? There are many reasons, we can talk about that philosophy later, but now something which is a decade old, we have not still adapted. Now we are going to talk about, and that is much more simpler to handle as a concept, as a technology, as a process than what we are talking for security, correct? Because there everything is at least open for us to understand. In security we don't know what is inside. We don't know what is, does anyone know about 1 million lines of Unix code? Even the original originator of Unix may not know. It's not that what a code does, what it does when it is interacting with other parts of code. So a security issue is not about just one piece of code but multiple components trying to do. Suppose there is a breach in say in a credit card swiping, that breach could happen because of 20 different vendors today. You understand? 20 different people are involved from the moment you swipe a card to the point it goes to your bank account and it says no, you get a approval, right? 20 different components are there. So if I talk about breach, somebody says no, for a breach you should be responsible. Somebody says it's not, we can't assign responsibility today. There are 20 different fellows who are involved and the fault can be on multiple people, the fault can be on no one, right? I have done correctly, he has also done correctly, but the way we both interact there is some fault. Now whom do we give the responsibility of this interaction, right? Correct? Right? Some major company says that they will keep the server in the sea, in some international waters, then they are not bound by the tax rules of any of the nations, right? If I keep it in international water, then it's not India, it's not China, it is not Pakistan, not anybody, so I will not pay tax to anyone, okay? You got my point? So if I keep my server and do business in international waters, then no country can claim tax, no? To which country will I pay? Right? So these type of, this is philosophically the question that we are trying to answer. So today security is becoming a very, very big issue, and for us to learn security we have to learn from the grassroots level. That's my call here. So that is why one of the lectures that I had sent, the YouTube videos and other things, which basically talks about all the 4 assignments that I have put here, those are the beginning points of making your system secure. And 5 to 10 years later, the biggest jobs will not be in your Uber or your Morgan Stanley or your Goldman Sachs, it will be in security. Even if you go there, it will be in security. So let us try and give you a vision about that, and that's what we will be covering here. Okay, so my whole thing will have a thrust on security, because that is what I feel is the next gen hot topic when you all go out into the market. You do cloud computing, you do data analytics, you do everywhere, there will be a security, there will be a privacy issue, there is some NDA that you need to sign, right? So you should understand those languages. I think I have to train you, and that is what we will be doing in this course. Okay.